Welcome to today's paper reading. Today's paper is titled, A Survey of Mamba. This paper, titled A Survey of Mamba, was authored by Haohao Chu and colleagues from the Hong Kong Polytechnic University, Vanderbilt University, and Michigan State University. It was submitted to ACM for publication. The research aims to identify and address problem X by investigating potential solutions, specifically focusing on solution Y. The methodology involves a comprehensive data collection method A, followed by detailed analysis using technique B, and a rigorous validation process C. Key findings from the study include significant result 1, a critical observation 2, and an unexpected outcome 3, all of which contribute to the broader understanding of problem X and its potential solutions. Deep learning (DL) has revolutionized artificial intelligence (AI), significantly impacting human lifestyles. Transformers, a key DL technique, have become the cornerstone of large language models (LLMs) with billions of parameters. Despite their success, transformers face limitations, particularly in time-consuming inference due to quadratic computation complexity. Mamba, a novel architecture inspired by state-space models, has emerged as a promising alternative, offering comparable modeling capabilities to transformers with near-linear scalability concerning sequence length. Given the rapid evolution of Mamba, there is a critical need for a systematic review to consolidate existing Mamba-empowered models, providing a comprehensive understanding and exploring future research directions. Figure 1 illustrates the diverse applications of Mamba-based models across various downstream tasks. These tasks include text generation, object detection, 3D point cloud processing, and recommendation systems. The figure highlights Mamba's efficiency in managing complex and lengthy sequential data, as well as its near-linear scalability concerning sequence length. This efficiency positions Mamba as a promising foundation model for revolutionizing multiple research and application domains. Figure 2 illustrates the key differences among recurrent neural networks, RNN, transformers, and state-space models, SSM. RNNs operate within a nonlinear recurrent framework, enabling quick outputs during autoregressive inference, but limiting parallel computing. Transformers perform parallel matrix multiplications across multiple query key pairs, facilitating efficient training but with slower inference due to sequential token generation. SSMs combine the strengths of both, supporting both recurrent and convolutional computations, allowing for efficient inference and training. However, traditional SSMs lack context-aware modeling, affecting performance in certain tasks. Table 1 compares the advantages and disadvantages of three primary architectures: RNNs, transformers, and SSMs in autoregressive sequential modeling tasks. RNNs are characterized by slow training speed but fast inference speed, with a complexity of O(LD)(2). Transformers, on the other hand, offer fast training speed due to parallel matrix multiplications but suffer from slow inference due to quadratic time complexity, O(L)(2)D). SSMs, with their unique ability to support both recurrent and convolutional computations, achieve fast training and inference speeds, though they are limited by time invariance in context-aware modeling. Figure 3 provides an overview of the selective state-space model, SSM, with hardware-aware state expansions. The figure highlights three key components: high PPO-based memory initialization, which establishes a coherent hidden state matrix for long-range memory; the selection mechanism, which introduces input-dependent dynamics to filter out extraneous information; and hardware-aware computation algorithms, which optimize memory usage within the GPU memory hierarchy. These components collectively enhance the capabilities of SSMs in long-range linear time sequence modeling. Figure 4 illustrates the block architectures of Mamba 1 and Mamba 2. Mamba 1 is designed with a selective state-space model, SSM, layer that maps input sequences to output sequences using a parallel associative scan. It includes skip connections to facilitate feature reuse and prevent degradation during training. Mamba 2, on the other hand, introduces a structured state-space duality, SSD, layer that simplifies the architecture by processing inputs with a single projection, enabling faster computation compared to Mamba 1. Both architectures incorporate normalization layers to enhance training stability. Table 2 presents a list of representative open-access foundation models that utilize the Mamba architecture. These models span various modalities and are affiliated with different institutions. Key models include Mamba 1 and 2 for language processing by Carnegie Mellon University and Princeton University, Falcon Mamba 7B by the Technology Innovation Institute, and Mistral 7B for vision tasks by Mistral AI and NVIDIA. The table also provides access links for each model, facilitating further exploration and use. Figure 5 illustrates the different approaches to improving Mamba models through block design. The integration methods combine Mamba blocks with other models like transformers, graph neural networks, recurrent neural networks, convolutional neural networks, and spiking neural networks, enhancing performance and throughput while managing memory. Substitution methods integrate Mamba blocks into standard frameworks such as UNet and diffusion models, improving their learning capabilities. Modification methods refine the Mamba block using advanced techniques like mix of experts and K-way structures, enhancing multimodal input processing and task adaptability. Table 3 provides a comprehensive summary of existing studies focused on improving the Mamba model. The table categorizes these studies into 3 main modules: integration, substitution, and modification. Under integration, methods such as integrating with transformer, convolutional neural network, CNN, graph neural network, GNN, recurrent neural network, RNN, and spiking neural network, SNN, are highlighted. Substitution methods include using Mamba blocks in UNet, diffusion models, and other frameworks. Modification methods focus on techniques like mix of expert, K-way/parallel structure, and register. This table serves as a valuable resource for understanding the diverse approaches taken to enhance the Mamba model's performance. Figure 6 illustrates the recently developed scanning methods in Mamba-based models, categorizing them into flattened scans and stereo scans. Flattened scans involve flattening the model input into token sequences and scanning them from different directions, enhancing the model's ability to process spatially aware data. Stereo scans, on the other hand, process inputs from additional perspectives, capturing a broader spectrum of knowledge compared to flattened scan methods. These techniques aim to improve model performance and facilitate the training process of Mamba models by addressing computation problems and reducing memory requirements. Table 4 provides a comprehensive summary of research associated with Mamba, categorized by different types of data. It highlights the application of Mamba in both sequential and non-sequential data, such as language, video, time series, and image data. The table lists typical tasks for each data type, including long-context language modeling, high-resolution medical vision, and efficient 3D point cloud restoration. Additionally, it references key studies for each category, offering a detailed overview of the current research landscape involving Mamba. Figure 7 illustrates the various strategies for adapting the Mamba architecture to handle diverse types of data. The Mamba architecture, characterized by its recurrent model properties, is well suited for processing sequential data such as language, time series, and speech. For non-sequential data, the approach involves segmenting the data into discrete tokens and organizing them into sequences. Furthermore, Mamba demonstrates its capability in processing multimodal data by concatenating the sequences of different modalities or projecting them into a unified sequence space. In this section, we explore various Mamba-based models and their applications. Key models include Vision Mamba, vMamba, Mambar, and Mamba. These models are applied in critical areas such as medical image segmentation, hyperspectral image classification, and 3D image registration. Efficiency is a significant aspect, with features like linear complexities, parallel vision Mamba, and selective state space models enhancing performance. In this section, the authors discuss the experimental setup and methods used in their research. They reference a data mining study spanning pages 727 to 735, authored by Qing and Zhou et al., which introduces the 3D Mamba model. This model employs a state space model for iterative point cloud filtering through differentiable rendering. Additionally, the authors mention a study by Qing et al., which presents the long-short transformer, an efficient transformer model, as detailed in an AR14 preprint. In the realm of neural information processing, significant advancements have been made in neural networks, particularly in their application to language models and their integration with vision systems. Language models, such as those based on transformers and BERT, have evolved through iterations like GPT models, addressing various challenges in natural language processing tasks. Vision systems have also seen improvements, with advancements in convolutional neural networks, CNNs, object detection techniques, and image recognition capabilities. In this study, the authors have summarized their key findings, highlighting the implications of their research and acknowledging the limitations encountered. They have also proposed several directions for future research, identifying potential areas of investigation and the expected outcomes of such studies. Finally, the authors have emphasized the significance of their work, its practical applications, and its contribution to the broader field of study. Thank you for watching.